Hello and welcome. In this video lesson, we're going to take a look at how we can improve the traditional Euler's method, and we'll look at two iterations of how this can be done. So one of the things that we've noticed is that Euler's method is extremely prone to error and compounding of error. And the reason for that is because when we use Euler's method, we're assuming rates of change are constant for some non-zero interval of time. And so even if that interval of time over which we're assuming a constant rate of change is really, really small, eventually all those little tiny errors will accumulate, even for small step sizes, and we will get inaccurate results in the long run. So then why do we really study it if we don't use Euler's method? And the reason is because Euler's method provides an intuition for what it is that we're about to do. So one of the major reasons for this is that we are assuming, again, a constant slope that changes more or less rapidly, which varies from function to function. One improvement we could make to this is to pick a slope which is perhaps an average of two slopes. So rather than use one slope and to assume that that's the best slope for the entire interval, let's pick two of them, and one at each end of our interval to cause us to diverge from the actual solution less rapidly as we increase t. So if, for example, we compute one slope and it's too high, and we compute a second slope but it's too low, then the average of them, in theory, should get us closer to the slope that's just right. This method, or improvement to Euler's method, is often referred to as improved Euler's method, or Hans method. I am not so much familiar with this name for it, but I'm guessing this is the individual who modified this. I usually think about this as Runge-Kutta 2. Now, Runge and Kutta were two mathematicians who came up with what we'll study soon, which is Runge-Kutta 4, sort of the default numerical method that we will use for precision. Runge-Kutta 2 is just a name for it because in a moment we'll see that it uses two slopes. So instead of our method resulting in one slope, recall that the way we did it before is we said to get the next value of y, we're going to take the previous value of y and add to it, depending on how big our change in time is, multiplied by our current slope. So what we did was, when we looked at this graphically, we said, okay, so here's our starting value, and we'll plug that starting value into our differential equation, which is f of t comma y. So this was some point t0, y0. It doesn't have to be times 0, it's just that's the way I'm drawing it here. So what did we do? Well, in this case, we went ahead and we computed f of t naught, y naught. So that's just the slope, right? That gives us a slope. And then what we did is we assumed that for some period of time, we'll just say that here's t naught, here's t1. Now that doesn't have to be 1 unit. That could be half a unit or a quarter of the unit, but this distance between these 2 points is actually what we refer to as the step size, the delta t, how long we're going to assume that constant rate of change for. So let's just suppose that we calculated the slope and the slope looked like that. It was a positive slope. So we assume that that positive slope is constant for that full interval of time, and we'll use that to calculate our next ordered pair, which is the point t1, y1. So this change right here, this vertical change that we have here, that is calculated by taking the change in time. So to get y1, we had to take the change in time, we had to take y naught, we had to add to it the change in time multiplied by how much we expect the change to be. So multiplied by this slope. So if this slope were, let's say, as an example, 3, if this were 3, that would mean that for a 1 unit change in t, we would expect a 3 unit change in y, But if our step were only a half, then we would estimate this red part to actually be 1.5, because half of 3 would tell you that if this were only a half a unit right here, that we would only expect half the rate of change increase. So that this generalization, now if we replace 1 and 0 with k plus 1 and k respectively, then that sort of tells us how we get from t1 y1 to t2 y2. It's just always using the previous information to get the next value. But suppose that instead of having just one slope here, which is what we have, what we did is we just replaced that one slope with the average of two slopes. So notice that this parenthetical quantity is just the average of two slopes. Why the average? We'll explore this a little bit more, but it just sort of intuitively makes sense. Let's average two slopes together. Now we're not going to call it slope 1 and slope 2. We'll call it k1 and k2. For the sake of just entertaining this idea, let's suppose, and so this would be our general form for that, now that we replace slope 1 and slope 2 with k1 and k2. So the real question is, well, what should k1 and k2 be? We'll prove that this should be true soon, but let's suppose that our k1 is just going to be the same slope as it was previously. So here's the actual solution curve. Now, if you take the derivative of the solution function, you get the differential equation that you started with. And so if that's the case, we're going to use the slope at our t0 value. Notice that t0 in this example is not shown as having to start at the y-axis. It could be at any point. It doesn't really matter. Now, this tangent line, this slope, the slope of that tangent line is given to us by the differential equation by plugging in this ordered pair right here, which without confusion should be the point t0, y0. And so we calculated that slope there, and then what did we do? Well, with Euler's method, we assumed that that slope was constant for some period of time delta t. You'll see that this picture and the picture that I've drawn here are virtually identical in the sense that we started off in Euler's method by using the slope at that point, projecting that slope forward, multiplying it by its step size to ensure that we get the right change, and that's just delta t multiplied by the rate of change per 1 unit of time. That gives us this next point t1, y1. Well, let's just entertain this idea that k1 will be the slope at the previous point. And I'll put previous in parentheses, or in quotes, because what I mean by previous in this drawing is t0, y0. K2 will be the slope at Euler's, the standard Euler's method, next point. So imagine, so like in this case, for the drawing, we would say this would be the slope at t0, y0. So that would be f of t0, y0. And so as an example, and the second point in this drawing, or the second slope we would get, is this, the hypothetical slope at t1, y1. Now we're not going to actually use that as our final t1, y1 because that's what Euler's method did. We're just going to grab a slope here. Then we're going to take this point, plug it into our differential equation, get the slope there. We're going to then average them together. So our formula, yk plus 1, will be y sub k plus delta t times, well, k1 is just the slope at the previous k, so I'll write this at f of t sub k comma y sub k, and that's going to be the average of that slope, and then the slope at the next point, which I'll just write as t sub k plus 1 comma y sub k plus 1. So all this means is that we just need to evaluate the differential equation at the next point. So if we were at t0 and t1, this would be f of t0 y0, and this would be f of t1 y1. But we're trying to make this as general as possible. And then we average those two slopes together. Okay, well this is all great, but it doesn't really give us an operable definition of how to calculate the next slope, right? We have to sort of think about how we obtain t1 and y1. Well, t1 is really just t0 scooted to the right over, or shifted over to the right by delta t units. So t1 is t0 plus delta t. Oh, perfect. So I've been able to rewrite t1 in terms of t0, which is known, and delta t, which is also known. Now I'm going to write this more generally. And more generally, we could write this as t1, or t sub k plus 1 equals t sub k plus delta t. Now for the y component, we know that to get y1, we have to take y0, and that's just this formula up here, plus our step size multiplied by how much change we expect per change in step size, or per 1 unit change rather. And again, we could do this generally just by replacing our subscripts as appropriate. Y sub k plus 1 is equal to y sub k plus delta t times f of t sub k y sub k. Great. So now I can actually replace the parameters in this equation here. I can say y sub k plus 1, and I can rewrite the right-hand side with everything being in terms of k and not k plus 1. So y sub k plus delta t times, and in parentheses I'm just going to write k1 plus k2 over 2, where, and now we'll go ahead and define these guys. We'll just say where k1 is just, again, the slope at our previous point, f of tk yk, and where k2 is the slope at the point tk plus 1 yk plus 1. But now I can rewrite tk plus 1 and yk plus 1 in terms of tk and yk. And don't worry, this will make a lot more sense whenever we look at an example of it. So this will be, okay, t sub k plus 1. So t sub k plus 1 is t sub k plus delta t. Y sub k plus 1 is y sub k plus delta t times f of tk yk. Okay, that seems like a lot, but here we have that summarized of what we just did. And you'll notice this is exactly the same thing that we derived here. It's a lot of substitution. It's attention to detail. But based on the fact that we picked these two slopes, again, one of them is just the standard slope that we would have picked in Euler's method. The second slope is if we had calculated t1, y1 by using the standard Euler's method, but then used that t1, y1 and computed the slope from the differential equation, and then averaged those two slopes together, this method applies right here. So let's take a look at an example. Let's compare Euler's method to improved Euler's method and see that it performs better for this equation, dy dt equals negative 0.4y, with y of 0 being 100, our initial condition, and we want to compare these two processes at time 4. Now this is fortunately a separable differential equation, and if you were to solve it and evaluate the initial condition, you'd get 100e to the negative 0.4t, and you have to use x here. And this just shows me that at time 4, I expect my y value to be at this exact value, 20.189652. All right, so standard Euler's method. To do the standard Euler's method, let's start with that one, just to recall what this looks like and how this works. So we calculated the slope, which is given by negative 0.4y. And because our step size here is 1, we don't really need this column, but remember delta y is the step size multiplied by whatever that dy dt was. And I'm going to write dy dt as f of t comma y. All right, so this guy here, another name for him is f of t comma y, and that's just convenient because we can see what values get plugged in. So here we have 0 and 100 for our starting value. And if you take negative 0.4 of 100, you get negative 40. Now, because our step size is 1, we're going to multiply that negative 40 by 1. Remember, that's a decrease of 40 elk per year. And we are going to advance 1 full year. So this is going to be negative 40. Again, like I said, we don't really need this column. So that means I'm at 100 elk. I expect to lose 40 elk, so that's going to be at 60. And now we'll repeat this, negative 0.4 of 60, which comes out to negative 24. Okay, and so again, I'll take 1 unit of time, negative 24 units per unit of time, which is negative 24. And so now that 60 is expected to decrease by 24 in 1 year, which comes out to 36. Taking negative 4.4 times 36 gives me negative 14.4. And again, 1 times that will give me negative 14.4. 36 is expected to decrease by 14.4, which is 21.6. Here we'll get negative 8.64, and same thing here. And so at time 4, my estimate using the standard Euler's method will be 12.96. Now, that value of 12.96 is not at all close to what we had expected of 20.19. So our relative error is quite large, or percent relative error, which is my estimated minus my exact, divided by my exact, multiplied by 100 to get it into a percent, comes out to negative 38.84%. Holy mackerel, that's huge. That's a huge error. And as a result, we wouldn't want to use a step size of 1. Now, this is fairly common with Euler's method, so nothing unexpected has happened here. But now let's go ahead and carry out the improved Euler's method. So what I'm going to do is I'm going to create some columns here. I'll have a number of columns. I'm going to have T. Try to use up the page here because this is going to take a little bit of space. So there's going to be a T column, and then there's going to be a Y column. And then there's going to be a column for K1 and K2, because I'm going to have to compute those slopes separately. And K2. Oh, and one thing that we forgot to point out back here in our general formula is that we're going to go ahead and use H instead of delta T. It's just a little bit more convenient, and these formulas can get kind of messy, so having delta T in here can be kind of messy. But you just notice that these formulas are in fact the same. We're just going to be using H instead of delta T. So we'll have a column for K1, a column for K2. Then we're going to need a column for the expected change in Y. And the expected change in Y is going to be the average, or it's going to be delta T times the average of these two slopes. So nothing different here, with the exception that we're going to average those two slopes together, whereas in Euler's method, we just take the one slope and multiply it by delta T. Okay, so at time 0, we know that there were 100 elk. To get K1, this is the same process as Euler's method. This is just your f of t and y, or whatever your current t and y is. So for the K1, well, K1 is just going to be the slope at that point, which is 0.4 times 100, which comes out to -40. But K2, recall that this is the funky one. This is f of, if I'm going to use t and y to represent the current row that I'm in, this value here is going to be f of t plus delta t, which we're using h for, and then y plus h times, as we see up here, f of t and y. So it's just going to be a multiple of that K1. Another thing you can do in here is, because these two things are the same, this thing here is really K1. So I suppose that in our final form, we could just refer to this as K1. So notice that these two are the same things. So what I'm going to do here is times K1. So I have to figure out t plus h. Well, h, recall, is our step size. So h is equal to 1 in this problem. If your step size was a half, you'd have to plug in a half for h. But to get K2, what we need to do is we need to calculate f of t plus h. So our current t is 0. 0 plus h, which is 0 plus 1 is 1. And y plus h, well, the y value is 100. Plus h, which is 1, times K1, which is -40. Okay, so we're not done yet. That's just the input into that function. So we need to calculate f of 1 comma -60. Okay, so what that means is that in my differential equation, which is f of ty is -0.4y, all I need to do is take -0.4 of whatever the y value is, which is -60. Note that this differential equation is autonomous. It doesn't depend on the value of t, but if it did, we might need to insert that 1 somewhere. And -0.4 of -60 comes out to -24. Okay, so that means that here are the two slopes. You can see one is a steep negative, one is a less steep negative. But to get delta y, what I'm going to do is I'm going to take delta t, which is 1, K1 plus K2, which is -40 plus -24 divided by 2, and that comes out to -32. So see, I'm being a little bit more conservative here. I'm not going to decrease that 100 by the -40, or decrease the 100 by 40. I'm going to decrease the 100 by a little bit less. So it's going to be a less extreme change than what we got up here when we actually did just use that one slope to decrease the number of elk, let's say, by 40. We're going to decrease it by 32 instead. So that means that time 1, I'm going to now have 100 minus 32, which is 68 elk. And if you look at the table of exact values, you see that we're a lot closer to that 67 than we were when we used just the one slope. So already this is showing some promise. To get K1, I need to take -0.4 times my current y value, because it is simply the slope based on the current ty pair. Again, t is not relevant because this is an autonomous equation, but this would come out to -27.2. Now, to do this next piece here, what I have to do is take f of t plus h. So my current t is 1. Adding 1 to my current t makes this f of 2. And now the y component as the input will be y, which is 68, plus 1, so that's my step size, times k1, which is -27.2, which evaluates to f of 2, comma, this will be 32.8. And so all that means is that I just need to plug in 2 for t and 32.8 for y in my differential equation. And again, t does not come into play, so it's just going to be negative 0.4 of 32.8, which comes out to negative 16.32. I caught myself with a minor mistake here. I wrote 60, but it should be 68, which changes this value here. That last one should be okay, actually. So this should be 68, which here this gives us 40.8, and negative 0.4 of 40.8 comes out to negative 16.32. So really we're showing this process to see that this formula, all it requires is the information on that one line in order to be able to come up with what the slope is. So once again, we're going to average these two together. So we're going to take delta t, which is 1. K1 plus K2 is negative 27.2 plus negative 16.32 over 2. And this is going to come out to negative 21.76. Okay, so that's the slope I'm going to use. That's the average of those two slopes. So 68 will be decreased by 21.76. And that will come out to, I'm going to need a little more space here. Okay, so this will come out to 68 minus 21.76 will give us 46.24. The K1 that we'll get is negative 18.5. The K2 comes out to negative 11.10. And then when we average these together here, we're going to get negative 14.80, following that same logic. Now 46.24 will be decreased by 14.8, which gives us 31.44, negative 12.58 for K1, negative 7.55 for K2. Their average is negative 10.06, so let's decrease 31.44 by that amount, and we're going to get, at time 4, an estimate of y of 21.38. And there is our estimate. Now, one of the things that we're going to notice already is that our exact value was 21.19. So our relative error, percent relative error, will be the estimated, which is 21.38, minus the exact, which is 21.19, divided by 21.19, and that comes out, and multiply that by 100, of course, that comes out to about 0.90%, which is a very small error. Very small error. And that is fantastic. That's exactly what we wanted. Now what we see is that improved Euler's method does produce less error in comparison to Euler's for the same step size. However, it's still going to compound the error because we're still making mistakes. It's hard to say how fast it will catch up to Euler's method, how many more units of time you'll be able to go before the error gets quite as big. But it will diverge from the actual solution, even for reasonable step sizes. So if this one's not that much better than Euler's in general, and it requires that much more computation, why are we doing it? Well, we're going to get at that question now. So should both slopes be weighted equally? Should they both be weighted at 1/2? Now the reason that we say weighted with 1/2 is because here, if you distribute the 1/2 in, K1 and K2 will both get weights of 1/2. We call those weights. Now we arbitrarily chose the slope at the current point and the hypothetical slope at the Euler's method next point, and we chose to weight both of them equally in the average. Note that you could always weight one term by, say, 1/6 and the other by 5/6. So when you take 1/6 of something and 5/6 of something else, you still get a whole, but you're placing 5 times more weight on the second term, or vice versa. Improved Euler's method is actually Runge-Kutta 2. What this means is that we will approximate the next y value by using a Taylor series approximation. So it seemed like we kind of arbitrarily picked the weights and we arbitrarily picked which slopes to use. Hopefully there was some intuition behind that, hey, yeah, let's average things together and let's use a slope at the beginning of the interval and at the end of the interval. So I think there's some intuition in that. But we haven't answered why we weight both of them equally and why we should be using those two particular different slopes. So we're going to be using what's called a Taylor series approximation. And I recommend this video highly. It's 22 minutes long, and you're going to find some valuable information there about what Taylor series is. I'll describe it here in a nutshell. So in a nutshell, what the Taylor series does is it's a way to take a complex function and approximate its shape in a neighborhood, using only polynomials, in fact. So, for example, for small angles, cosine of x, which is called a transcendental function, it's actually really hard to get calculators to graph these functions, believe it or not. And you can actually approximate cosine of x for a neighborhood, meaning for just values very, very close to x equals 0, by using the function 1 minus x squared over 2. And that's a first order or second order Taylor series expansion. So what you notice is that the red graph here is cosine of x, and the blue graph is 1 minus x squared over 2. And you can see that from about here to about here, we have that blue graph provides a really good approximation to cosine. So as long as your angle is theta is between somewhere, I don't know, negative 0.8 less than or equal to theta less than or equal to 0.8, or maybe not theta, but x, we use x instead, then for x is between these values, the blue function does a really, really good job of approximating the values on the red curve. So, but it's a much easier function to work with. So if you know you're going to be working with small angles, then you could replace the function cosine x with 1 minus x squared over 2. The reason we like polynomials is they're easier to differentiate. Quadratics have nice formulas like quadratic formula. Polynomials are just in general much easier to work with. So 1 minus x squared is a second order Taylor series expansion, or TS2 if you will, to cosine of x. We can increase the order and find an even better fit. This is called a fourth order Taylor series expansion, and now you see that so this is second, this is fourth, and you can see that the green curve expands the domain. You can actually see that it's a really good approximation from there to there, whereas the blue curve is only a really good approximation from about there to there, as we saw in that previous illustration. So increasing the order of the Taylor series basically just creates more curvature to contour the function you're working. And that's all a Taylor series expansion really is. It's creating a polynomial that basically increases and decreases more and more often as you increase the order, because if you take a quartic, it can change direction, let's see, 1, 2, 3 times. It changes direction. And so if you did a fifth order, it could change directions up to 4 times, giving that think about that function as being more pliable or more flexible. So that's kind of what a Taylor series does in a nutshell. We're not going to derive this, but again, if you watch that video, you'll see the beautiful derivation of this. But if we want to approximate a function, it doesn't have to be near x equals 0 like it was. Let's say we want to approximate it near x equals a. So, again, if we were looking at the cosine function and we wanted to approximate it at x equals pi halves, and we wanted to find something that fits sort of this portion of the function here, then we could do that. So our a in this case would be pi halves. Okay, so you can see how this pieces together, and this just says plus dot dot dot. And the reason for that is because the only way to get these to be exactly the same is by having infinitely many terms. We're, of course, not going to keep infinitely many of them because that's no more practical than trying to use a complicated function. The more terms we keep, the more accurate the approximation, though there is a practical to complex trade-off after about the fourth order term. Now, we don't do f prime, 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 prime. We usually just say f with a 4 in parentheses, so it doesn't look like f to the fourth power. That's the fourth derivative. So you really just gain way more complexity than you do benefit after the fourth order terms. But let's just keep this really simple and say we only took the first 3 terms. So we went up to the second order derivative. Now notice that my sign here is no longer equal to, it's approximately equal to. How approximate? Well, it's going to depend on the function, depend on the point. It really just depends. So we could get a really sloppy approximation or a really good one, but this is better than none. Now, so this is an approximation to a function. The function that we want to estimate is, recall that we want to find y sub k plus 1 based on y sub k plus some delta t. I'm going to stop using delta t, I'll use h, plus h times some proverbial slope. Okay, so we want to estimate that proverbial slope to get y sub k plus 1 to be as exact as possible. Now, y sub k plus 1 doesn't look a whole lot like the notation here, so what I'm going to do is I'm going to go ahead and write y sub k plus 1. What that really means is the y value at our current value of t plus a step size, right? So basically this is the y value at some point. If I call this t, and t plus h is over here, what I want to do is, based upon this point, I want to estimate this next y value over there. So this y value here is y at the t coordinate t plus h. So I want to estimate this. Now, that's kind of like my f of x. That's what I want to estimate on this side. So what I'm going to do is I'm just going to say, all right, well, this is analogous to saying I want to expand y of t plus h. Now this point right here is central to the function, and so I'm gonna write almost without too much justification here that this term is going to be like our y of t. F of x is the actual function. F of a is the function evaluated at the current point. So I'm going to kind of write this without a little bit of justification here because it does require some limit thinking. But x minus a, this is going to be an accurate approximation if this quantity here is infinitesimally small, and we often call that h. So 1 factorial by definition is 1 times 1, or just is equal to 1. So this will be h, x minus a, we're going to replace that right there with h. And a is our current value of t, so we'll write f prime of, sorry, not f prime, but y prime of t. And we'll do the same thing over here. Here is h, we want that to be really, really small. And 2 factorial is 2 times 1, so this will be h squared over 2 times y prime prime of t. Now, recall that one thing that we wrote is that dy dt is a function of both t and y. So in order to compute its second derivative, or we could say y prime equals f of ty, its second derivative will be, we've got to use the chain rule here. If you haven't taken Calculus 3 yet, this derivation may not make a whole lot of sense for this given moment, but if I want to compute the derivative of a function that depends on 2 inputs, which is y prime, we could use the multivariate chain rule, and we have that y prime is a function of t, and it's a function of y, and y itself is a function of t. So with each of these little chains, they're all, in order to find the rate of change of y with respect to t, in other words, to find y prime prime, I have to follow the chain all the way down and take the derivative of y prime. Remember, y prime is f of ty, so I have to take the derivative of f with respect to t, and I also have to follow the chain this way, which will take the derivative of f with respect to y, and this link here, take the derivative of y with respect to t. So this is going to be df dt plus df dy times dy dt. And you can see that, that if you cancel out the dy's here, you end up with df dt plus df dt. And what this essentially means is there are two different contributions to how y prime changes. It changes from a change in t as well as from a change in y. And so another way we could write this is y prime prime equals f sub t of t and y plus f sub y of t and y multiplied by dy dt, which is just y prime. Now even y prime can be written as f of t comma y. So I have this notation, which again, this looks very daunting because there are a lot of symbols here. We just need to remember what these are. This is the first derivative, which is just f of t comma y. Now what I'm going to do here is, so I would just establish that y double prime is f sub t, t comma y, the partial of f with respect to t, plus the partial of f with respect to y, multiplied by f of t comma y. So what I'm going to do in this form now, and we're getting closer to the solution, is I'm going to say that y of t plus h is equal to y of t plus h times y, instead of y prime of t, I'm going to use f of t comma y, and plus h squared over 2 times what y double prime is, which is this whole expression. So that's just a substitution step. And we're very, very close to actually seeing this as your next y value is your previous y value. Notice that this is the very first slope right here. This is what we call K1, or pretty close to K1. We're going to do one more thing here, and this might not be something that you're familiar with, but the multivariate Taylor series expansion is going to look like this, that if you have y of t plus h, f of t plus h, f of t plus h, comma, y plus k, that this is going to come out to f of t comma y, f of t comma y, plus now this is going to be h times f sub t with respect to t and y, plus k times f sub y with respect to t and y. And you notice that this is really just the same thing as the original Taylor series expansion, except it includes a term for both the t component and the y component. But this is all we really need. And I'm going to do one little trick here. The f of t plus h, if instead of having y plus k, I had y plus h times f of t comma y, if I had that in place, then all I would have to do is replace the k with this expression here, h f of t comma y. And the reason I'm going to do that is because this will allow me to make a substitution in our expansion up until this point right here. So we're trying to condense this down a little bit. And I see that what's on the right-hand side here looks similar to this, except that we're off by this extra term. So here I have k being replaced with h times, I'm going to replace k with, here's our k, right? Here's our k, and our k is really this extra plus piece. So now I'm going to replace k with h times f of t comma y, and then that still multiplies f of y comma t comma y, plus etc. This will give us an exact expansion for this multivariable function. So this is the same thing except for multivariable functions where you're in 3 dimensions and you want to approximate a 3-dimensional surface instead of a 2-dimensional curve. So you can see that from up here that what we have with respect to these terms here looks pretty similar to what we have down here, which means that I should be able to replace that. And I should have been using approximately equal to all the way along because we are approximating this with only the second order term. So if I factored out an h from here and I factored out an h from here, what this would give me is y of t plus h is approximately equal to y of t plus h times quantity f of t comma y plus here I'll just have h over 2 times f of t, so distribute, well, we factored out an h, so we don't have h squared anymore, but I have h over 2, which will distribute f sub t of t comma y, plus h over 2 times f sub y of t comma y, times f of t comma y. And what we should see from this is that this, again, resembles very closely what we have right here, with the exception of that factor of 2. I'm going to argue that if you rearrange this a little bit more, you'll have y of t plus h is approximately equal to y of t plus h over 2 times f of t comma y plus, and this will be h over 2 times f of t plus h, y plus h of f of t comma y. And so what we're getting at here is that this is approximately equal to y over t, y of t. Now if I factor out an h over 2 from both of these two terms, what I have left inside of here is, notice that this is just k1. That's what we've called k1, and this piece here, this is what we've called k2. And now you can see that what we have as the second order Taylor series expansion, the same answer is obtained, though this answer is one that is derived mathematically for the best weighting of the two slopes. This answers our two bolded questions from above. So I realize there's a lot going on here, and you don't necessarily have to be able to rederive this, but at least seeing how we kind of do these types of things might be beneficial to seeing. So our intuition was right. Let's use the beginning and end slope, and let's average them together, giving them equal weights. So this is a Taylor series expansion, but we notice that it still has error in it. So we might want to say, well, how many slopes should we actually use to improve or weed out as much of the errors as we can? As it turns out, you can run the Taylor series expansion as fourth order, which is going to involve a fourth derivative. It's going to have these progressive terms like we had up here, except it'll have f triple prime and then f quadruple prime. But if you don't really want to go beyond the fourth derivative because the precision gain is really negligible, but the workload grows considerably. So we stop with 4 terms and we call it Runge-Kutta 4, named after Runge and Kutta, and 4 because it's fourth order. So the basic Euler's method is really a Runge-Kutta 1 because it only uses the first slope there, k1. In Runge-Kutta 2, we use the k1 and a k2. But here we're going to use 4 different slopes. So k1 will allow us to calculate k2. K2 will then allow us to calculate k3, which will allow us to calculate this slope k4. And whenever we combine them in just the right way, we get a weighted approximation. So the weighted approximation of these 4 slopes that we're going to use, so notice that 2 of them are endpoints of the interval, xk and xk plus 1, and that 2 of them are sort of these halfway in between slopes. And this is just derived using a Taylor series expansion. You might say, well, why are we using the 2 intermediate slopes in the middle? And the reason is because of the Taylor series expansion. But the weird thing here is that notice that it still takes on that same form. Y sub k plus 1 equals y sub k plus h, that's our step size. But instead of saying 1/4, of the 4 slopes, we're actually going to give K2 and K3 double weights. So notice they have coefficients of 2. So we have 1 plus 2 plus 2 plus 1 is 6. So there are really 6 slopes lingering in here because it's really K1 plus K2 plus K2 plus K3 plus K3 plus K4. So we just get K2 in there twice and K3 in there twice because they hold more significant weight. H is the step size. Here are how the K's are calculated. In much the same way of the improved Euler's method, we're not going to do this by hand because it is extremely cumbersome and extremely prone to mistakes. So we're going to use technology in order to do this. Recall our ODE in example 1. We did this with with Euler's method, improved Euler's method. Euler's method really killed us. It did not provide good approximations. Improved Euler's was within 1% of the correct answer. To do a Runge-Kutta 4, we'll just go into Wolfram Alpha. So you can type in Runge-Kutta 4, and then we'll list the differential equation. You could do dy/dt if you want. This is just a little bit shorter. With the initial condition y of 0 equals 100. And then we want from t equals 0 to t equals time 4. And a step size of 1. So that's how we would input that process in here, and we just need to check the input, make sure it's been interpreted correctly. So solve that differential equation with that initial condition using 4th order Runge-Kutta method, the step size of 1 from y equals 0 to 1, this should be t equals 0 to 4, I'm not sure why it does that. In the solution plot, you see it plots the numerical and the exact solutions. That's the same curve that we saw earlier, but look at, you can't even tell the difference between the two. That's what Runge-Kutta 4 will get us. And we see that at time 4, the step size of 1 gets us to a value of 20.20. Now we see here that even for the step size of 1, this y value at time 4, the exact, recall, was actually 20.19. 20.19. So look at how close we are. We have nearly 0% error, and that is by picking a step size of 1. So already we can see that Runge-Kutta behaves a lot nicer to us than does the other one. So how small of an h is really necessary? We usually keep it at about 0.01 unless you're shooting for super high precision. Anything below that, and you're not really getting much gain in precision based on what we do in this lesson and in the following lessons. And computers can get really bogged down because it has to compute 4 slopes just to make 1 iteration. That's a lot. But then one thing that we get out of this is that now we're going to use Runge-Kutta 4 as sort of our go-to numerical tool. From here on out, we're going to use Runge-Kutta 4 if we're going to use a numerical tool at all. We can continue to decrease our step size and just check the error, make sure that step size of 0.01 is sufficiently small by choosing 0.001 and checking to see whether the change in the value that we get is considerable or not. We're going to do that next for an example. One that would actually be quite difficult to solve otherwise, and this will be our last problem. Consider a large pond that has a stream feeding into it and a stream leading out. Okay, so here's what we have. Here's our stream, our pond. We have stream leading in, stream leading out. Suppose that water flows at a rate of 1,000 gallons per hour. So here we have 1,000 gallons per 1 hour. And flows out at the same rate. So 1,000 gallons per 1 hour to keep the water level constant. However, suppose that the number of salmon swim in at a variable rate. So rather than there being a chemical coming in, what we have here, there's my best drawing of a fish I can possibly draw. We have fish coming in, right, instead of a chemical coming in. So instead of being grams per gallon, they're actually coming in at a variable rate of change of, okay, so 0.4 sine of pi 12ths t. If I look at the rate at which fish are coming in, fish per gallon, or salmon per gallon, versus the the time, right? Because this rate depends on time. We see that this will ensure that we have a center line of 0.8, and the number of salmon will fluctuate like this throughout the day. In fact, after a 24-hour period, it'll complete one oscillation. And so it'll go as high as 1.2 and as low as 0.4 fish per gallon. So what I'm going to do with that is, even though that's a function, and now this is why we're using Runge-Kutta for, because our input concentration, so to speak, of salmon is 0.4 sine of pi over 12t plus 0.8. And the units of that are salmon per gallon. So for every 1 gallon of water that comes in, there are quite a few salmon, right? So anywhere between 0.4 up to 1.2 salmon come in to the pond per gallon. Now this could be in hundreds, thousands, etc. It doesn't really matter. We're not going to worry about the decimals. But if I multiply these two rates together, notice that I get salmon per hour. And that's what I'm going to want to keep track of. Y is the number of salmon in pond. T is the time, number of hours after 6 a.m., time since 6 a.m. This will be in hours. And at 6 a.m., suppose there are 500 fish in the pond. So y of 0 is 500, and the pond contains 20,000 gallons. Using RK4, estimate the number of fish in the pond at 3 p.m. on the first day. Be sure that your answer is chosen so there is no more than 0.1% relative error from the previous step size. So we're always going to do like step sizes of 1, 0.1, 0.01, 0.001, etc. No reason why you couldn't just jump to a step size of 0.001, only that we just want to see how much accuracy would improve. And going from 0.001 to 0.0001 can really bog down a computer. Okay, now what's coming out is the same type of idea. We want to get this in salmon per hour, so this is going to have to be salmon over gallons, so that our gallons cancel out. And inside of the pond at any given moment, there are Y salmon inside of there. And how many gallons? Well, there are always 20,000 gallons. Now, dy dt is going to be the difference between the rate in, which is going to be 1,000 times this expression. So if I distribute that 1,000 in to this expression, I will have, let's see, that'll be 400 sine of pi over 12t. And then 1,000 times 0.8 will be 800, minus what's coming out, which will be 1,000 over 20,000, or 0.05y. Now you can see that this gets significantly more complex. This is non-separable. You can't factor this into a t and a y term. And then we'll also state that the initial condition is y of 0 equals 500. So here's the fun part. We get to now model this in Wolfram Alpha. So here we are inputting the equation. Again, just similar process. Notice that time goes from 0 to 9 because 3 p.m. is actually 9 hours after 6 a.m. So 6 a.m. to noon is 6 hours, and then noon to 3 is another 3 hours, and 6 plus 3 is 9. So there we go, just a review of what's going on here. Here's the actual number of fish over time. We see that there's kind of almost like a logistic type of curve where the rate seems to be slowing down. We have sort of this concave up piece here. And we see that at time 9, there should be 8,298 fish or thereabout. 8,298, that's a step size of 1. So the relative error is going to be shown here by looking at what happens when h is set to 1 versus when h is set to 0.1. So if h is set to 1, at 3 p.m. we see that there are estimated to be 8,298 salmon. And then all I've done is I've just gone ahead and set the step size to 0.1 and rerun this, and notice that the answer at time 9 is the same. So what does that mean? That means, therefore, increasing or decreasing step size in this problem does not result in a different output, a different a number of salmon at t equals 9. So our estimate is that at time 9 there will be about 8,298 salmon in that pond. So you can see we were able to model really quickly a complex phenomenon, and choosing our step size because we didn't have the solution to which we could compare our estimates. We simply had to run the Runge-Kutta with a decreasing step size and see if we get any observed change in the output. We could also just go ahead and, for the sake of entertaining this, change the step size to 0.01. And once again, because we didn't notice a change from h equals 1 to h equals 0.1, we're probably not going to notice any significant change here either. So as soon as this thing runs, you can see 8,298.14, same estimate, and the number of salmon predicted does not change. Therefore, we're pretty confident that we would expect about 8,300 salmon by 3 p.m. swimming around in that pond. So if you want to go fishing, good time to go fishing.